Hello and welcome to Unit 5, Atomic Structure, Lecture D. Today we're going to start talking about nuclear chemistry. So the first thing we need to talk about is what is radioactivity in the first place. And all it means is something is radioactive. It means that it will spit out subatomic particles. So particles smaller than the whole atom are being given off. And subatomic particles listed on reference table O. We talked about this earlier. Top number's the mass, bottom number's the charge. The ones that you're responsible for are listed here. Remembering that a beta particle is just a free high-speed electron, so electrons would also count. But alpha particles, it's a helium nucleus, so it's basically a helium with no electrons on it. Beta particle, again, a high-speed electron, mass of 0, charge of -1. Gamma radiation isn't a particle, it's just the energy that's given off. This is the very dangerous thing. This is extremely damaging to your body and the tissues. Everything that's radioactive gives off this radiation as well. It's the energy that's released when these particles escape from the nucleus. Neutrons, mass of 1, charge of 0. Protons, which is a hydrogen nucleus. So alpha particles, helium nucleus. Proton, hydrogen nucleus. And then a positron is antimatter. It is the equal and opposite of a beta particle. So it has a mass of 0 and a charge of +1. There are many other subatomic particles. These are the ones you're responsible for in chemistry. So when we look at the periodic table, we said earlier that the ratio of protons to neutrons to be stable would be 1:1. And the farther away you get from that 1:1 ratio, the more unstable it is. And that in the nucleus, you're trying to hold all of these positive protons together, but like charges repel, so it takes a lot of energy to try to hold them in there. When we get larger nuclei, they tend to be more radioactive because it's harder to hold all of those pieces in there together. If we look at the periodic table, we had said that the masses were a weighted average. But as you go through and you get to the larger particles, so you get over 83, here's polonium, his mass is in parentheses, so is astatine and radon. They're in parentheses because they don't have stable isotopes. We can't get a percentage of which isotopes there are in nature because they fall apart so quickly. So because they can't get good numbers, they just kind of get average numbers. So 83, anything bigger than 83, here you have 84 and over, they're radioactive, their masses are in parentheses. Notice that here in the middle, technetium also, mass in parentheses, they would also be radioactive. So if a multiple choice question asked you which of the following is radioactive, you are looking for something on the table that has its mass in parentheses, the largest out of all of them, possibly, and also anything on reference table N are radioisotopes. These are isotopes that are radioactive. So for example, carbon, small, its atomic number is 6, so that's way less than 83, normally stable. Carbon-14, however, is a radioactive isotope. So it is an isotope of carbon that is radioactive. So large elements tend to be more radioactive. You get farther away from the 1:1 ratio. Radioactive elements tend to have their masses in parentheses. Some of the isotopes of stable atoms are also radioactive. So if nothing in a multiple choice question has its mass in parentheses or is really, really large, then go to table N and look for those. The three big particles for radioactive emissions would be alpha, beta, gamma. So the first three letters of the Greek alphabet, alpha, beta, gamma. Alpha, you're going to write it as an alpha particle or as the helium nucleus. So mass of 4, charge of +2. This means that it's made of 2 protons and 2 neutrons. That's how it gets a +2 positive charge, but a mass of 4 altogether. It's a helium nucleus. It's the heaviest one, and we can stop this stuff with paper. So you can just wrap something that's spitting out alpha particles in paper. The paper itself will stop it. Your skin will stop alpha particles. So this one isn't as dangerous. Beta particles, however, so you have a beta symbol, and a lot of times you put a beta negative there, or something that is a high-speed electron, charge of 0, or charge of plus, mass of 0, charge of -1, high-speed electron. So he is a high-speed electron, and he is moving faster. So he's small, charge of -1. And we can stop this with metal. So aluminum foil or thicker metal will stop beta particles. It can get through your skin. Beta particles are more damaging to us. They can get through your skin and harm your body tissues. But we can block them with aluminum foil or other metals. Gamma radiation, on the other hand, so a gamma, no mass, no charge. It is not a particle. It is energy. All things that are radioactive give off the gamma radiation, and this stuff can only be stopped with lead or 3 feet of concrete. This is the really damaging stuff. When something is radioactive, it's not necessarily the alpha particles or the beta particles that are harming you. It's this gamma radiation that can go through and really damage the tissue. So when you get an X-ray and they drape you with the lead sheets, it's to stop the radiation from getting inside of your body. Of course, it gets through in the other parts, and there's always natural background radiation. So things like X-rays are something that your doctor is going to try and limit the number that you get. But we do always have some amount of radiation bombarding us all of the time, and so we try to limit how much we get, and our body can fix and correct some of the damage from the natural amounts. So we don't want to do anything to add to that so that we have more radiation than we normally would. Oh, say like tanning beds. All right, how did we figure out what these 3 most common subatomic particles are? It goes back to Ernest Rutherford, his gold foil experiment. After he figured out that atoms were mostly empty space, he continued to study these radioactive materials. And did more experiments with them to try to figure out exactly what they were. So he used a lot of electromagnetic fields, which will build up charges, and we know that opposite charges attract and like charges repel. So this yellow beam is getting bent up towards the positive plate, so that tells us the yellow beam must have a negative charge. This green beam is getting pulled towards the negative plate, so we know the green beam must have a positive charge. And then, of course, this red one must be neutral. In the materials that Rutherford was using, he then identified these pieces that were getting separated, and the negative ones were his beta particles, and the positive ones are the alpha particles, and the ones that were going straight through were the gamma rays. You can also, in other cases, the ones that are going straight through could also be neutrons, because they also do not have a charge to be attracted to one side or the other. In Rutherford's work, it was gamma rays. So if you can remember that opposite charges attract and like repel, you should be able to identify which particle it is using table O and using the opposite charges. Very common test question to give you this diagram without these labels and have you identify which it is. They'll label them A, B, C, and they'll say, what could letter C possibly be? And then you'd use table O, and you need to find something with a positive charge. It's not only alpha rays. This one could also be protons, because protons have a positive charge. There's another reference table that we use for nuclear chemistry, and that's going to be reference table N, which we've looked at a couple of times already. So let's go back to table N, pull it out, and I will explain to you what's on there and what decay mode means. So in reference table N, we have selected isotopes. So you already know that these are all things that are radioactive. They have this column here that's half-life, which we're going to talk about in Lecture E. So half-life for Lecture E, talked about half-life in earth science. The next column says decay mode. So the particle emitted during radioactivity is called the decay mode. And the way this works is if I have carbon-14, so carbon, mass of 14, the atomic number for carbon is 6. You probably have that memorized now. This carbon-14 is naturally radioactive, so it spits out a particle. What particle does it spit out? It spits out a beta particle. So if I go to table O, I'm going to use this notation here with the E for my beta particle, and I'm going to include those numbers, just like I have the numbers on my carbon. So my beta particle that it's spitting out, so that's the beta particle, which the decay mode right here is telling me that's the beta particle. I can figure out what the carbon's going to turn into. This top number is 14. On the left-hand side of the arrow, so this is kind of like balancing equations, I have 14 for that top number. On the right side of the arrow, I have 0 plus blank. So the top number over here must be 14 as well. On the bottom, I have 6. On the right-hand side, I have negative 1 plus blank. So what plus negative 1 gives me 6? 7. Now all I need is my periodic table. Element number 7 is nitrogen, so the symbol that I'm going to use is N. So when carbon-14 decays, it gives off a beta particle and turns into nitrogen. Easy enough? Okay, let's do another example. Let's pick something that gives off an alpha particle. So if we use francium-220. Francium-220. I need to know his atomic number. I don't have that memorized, so that's what my periodic table is for. Francium is in group 1 all the way at the bottom, so way down here. He is atomic number 87. He's atomic number 87. And my decay mode says he's giving off an alpha particle. So an alpha particle, don't have that memorized yet either. I go to table O. I find alpha particle. It's my helium nucleus. So the top number is 4 and the bottom number is 2. Top number is 4, the bottom number is 2, and the symbol is He. And then I need to figure out what francium's turning into. So on the left I have 220. On the right I have 4 plus what? And it has to equal 220. So that's going to be 216. On the left I have 87. On the right I have 2 plus something, and it has to equal 87. So that's 85. And all I have left to do is figure out which symbol to use. So I go back to my periodic table, and 85 is way over here on the right-hand side, and the symbol is At. And that's it. Simple as that. We're just adding, subtracting numbers, and using our periodic table to look up symbols, and using table O to look up symbols. That's all there is to it. These are things that are naturally radioactive, and we call this natural transmutation. We're transmuting from one element into another element, and since it happens naturally, they call it natural transmutation. So that's the first type of nuclear reaction you need to memorize. Natural transmutation. There are going to be 4 nuclear reactions that you need to memorize. They all give off large quantities of energy because a very small amount of mass is getting converted into energy. So that E equals mc squared equation way back from our introduction unit is coming back, and this is where it happens. Transmutation means we're turning one element into a new element. Natural transmutation means it happens all on its own. So here's an example. Uranium-238 turns into thorium because we have 234 and 4, and 92, 90 plus 2. All of our numbers add up. Uranium turns into thorium 234 by giving off an alpha particle. This is natural transmutation. There is only one reactant. One thing on the left, natural transmutation. One thing on the left, natural transmutation. Memorize it. If we have to shoot a particle in to get it to turn into something else, then we call it artificial transmutation. So if you have two reactants, sometimes you'll get two products, sometimes you'll only get one, but the key here is two reactants. If you have two reactants on the left, it is artificial transmutation. And again, we're adding up the numbers. It gets tricky when you have two things on both sides. 14 and 4 is 18, 16 and 2 is 18, 7 and 2 is 9, 8 and 1 is 9. The numbers just need to add up. When we're doing artificial transmutation, we tend to use particle accelerators. I know that's spelled wrong, so those of you with better spelling can put it in your notes correctly. What they do is they push and pull the particle using charges. So they rotate the charge, they spin it. So if you have an alpha particle, you spin a charge and have it spiral out. When it's positive charge near your alpha particle, it's going to push your particle because like charges repel. And when there's a negative charge near it, it's going to pull your alpha particle because opposite charges attract. And by rotating that faster and faster, they can push the particle faster and faster and faster until it reaches extremely high speeds. You need extremely high speeds for these particles to smash into the nucleus of your target atom. It's very hard for them to get past the electrons that are moving around the outside. They call that the shielding effect, where you have all of these electrons shielding your positive nucleus in the middle. We need to get these particles going fast enough to get past that shielding effect to break the nucleus in the middle. In this case, it's severing the nucleus, it's breaking it, it's splitting it in half. In this case, it's getting captured. When they're shooting this beta particle in, and we only get one product back, when the beta particle hits the nucleus, it gets absorbed. And instead of splitting the nucleus in half, it gets absorbed into the middle of the nucleus and makes a new element. Natural transmutation, one reactant. Artificial transmutation, two reactants. Fission is exactly like what it sounds like. So we talked about fissures in earth science, which are cracks or splits in the crust. This is going to be a large nuclei that gets split or cracked into two or more pieces. Specifically, fission that we're going to talk about is uranium being split in half by a neutron. So the first thing we have to see here is that a neutron is neutral. We can't use a particle accelerator to propel it. They have to use a little mini nuclear reaction to get this started. So it's really expensive to start a nuclear reaction in the first place using fission because you need to make a little tiny nuclear bomb. Basically, they make a little hydrogen bomb and it spits out this high-speed neutron. Once the neutron gets absorbed by the uranium, it gets absorbed into its nuclei. The nuclei is super unstable. It breaks apart into pieces, typically barium and krypton, and it spits out 3 neutrons. If you're adding up the masses, please be very careful. So 238 and 1 is 239. On the right side, we have 152 plus 84, which gives us 236. And you have this neutron that has a mass of 1. But notice that there's 3 of them. So what we're really adding is 3 for the 3 neutrons to get our 239. So watch out for that, especially if what they want you to do is, say, fill in the mass of the krypton. you have to remember that there are 3 neutrons over here. Okay, if we're only putting in 1 neutron and we're spitting out 3 high-speed neutrons, there are lots and lots of uranium atoms in our fuel. So these 3 neutrons then hit 3 uranium atoms, get absorbed and split. Each of the 3 spit out 3 neutrons. That gives you 9. Those 9 are going to hit nuclei and each spit out 3. That gives you 27, and so on and so forth. So it becomes a chain reaction. And the reaction keeps going all on its own. So once we start this fission reaction, it's expensive to get it started, but once we start it, it keeps going all by itself. If we let this go uncontrolled, it will create more and more energy until the neutrons are going so fast that they don't get absorbed by the uranium nuclei anymore, and then the reaction stops. This is the reaction that happens in a uranium bomb. So in a nuclear explosion, this is what happens. The neutron gets shot in, and the chain reaction goes uncontrolled, producing huge amounts of energy very, very quickly until the neutrons are going too fast. The uranium fuel doesn't get all used up. The neutrons just start going too fast for the reaction to happen. We use this, of course, as a weapon, but the original idea was to be able to control it and use it to make electricity. So let's look at the parts of a nuclear power plant. And briefly, let's discuss how a power plant works. So when we make electricity, we have some kind of fuel that produces a lot of heat, which turns water, so our coolant is typically water, into steam. That steam goes past turbines. So turbines are big magnets that spin through coils of wire. You may remember doing this in middle school, where you produced electricity with magnets in the coiled wire, or maybe it's 5th grade that you do the electricity unit. So we have these huge turbines spin and it produces electricity. Then the water can just recondense and be reused again. Okay, so you have this container where you're burning your fuel. Typically we burn coal or fuel oil. Uranium in a power plant uses a lot less fuel. So in the long run, it's very, very cheap to make the electricity, and the volume of waste product that you have left over is very small, and you don't have to worry about air pollution because we're not burning things in the normal way and putting particulates or CO2 or any of the other nitrates and oxides and sulfides into the air that are typically associated with a coal-burning power plant. So how do they control this nuclear reaction? Well, the first thing you need are your fuel rods. The fuel rods in here are red. Those are going to be your uranium. And they leave gaps in between, and in between the gaps they put in these control rods. The control rods are made of cadmium or boron, and they're special because they have the ability to absorb neutrons. So if this reaction is a chain reaction, it goes faster and faster because the neutrons are shooting in. If we can take some of those neutrons out, we can control how fast or slow the reaction goes. So they drop these control rods higher or lower, and that will speed up or slow down the reaction. The farther the control rods are in between the fuel rods, the more neutrons they absorb and the slower the reaction goes. They never let the reaction completely stop once it starts unless they need to inspect or check or change the fuel rods because it's so expensive to get the thing started in the first place. If there's an emergency, these control rods should drop completely in between the fuel rods and absorb all of the neutrons and stop the reaction. This is the part that broke at Chernobyl. When they were running tests on the reactor, one of the fail-safes to drop the control rods didn't work. The emergency one clicked in, and it had gotten so hot by that point because they were trying to test something that some other part broke or melted, and when the control rods dropped all the way in, they dropped in at an angle and got stuck, and they couldn't drop them all the way in between, and so they couldn't stop the reaction. the neutrons in here can get so fast that they go right past the nuclei and don't get absorbed. That would also start to stop the reaction. So they put in a moderator whose job is to slow the neutrons down. So that's what the moderator does. It keeps the neutrons moving at the proper speed. So you want them fast enough for the reaction to keep going, but not so fast that they're just going to glance off of the uranium. The coolant going through here is usually water or heavy water, because the heavy water can absorb more energy. So, of course, people want to know what heavy water is. Heavy water's formula is still H2O. That's not a problem. There's nothing different with the formula of the heavy water. But in regular water, your hydrogens have a mass of 1, and your gram formula mass is 18 grams per mole. 2 hydrogens at a mass of 1 plus 1 oxygen at a mass of 16, 18. In heavy water, your hydrogen is typically an isotope called deuterium. It has a mass of 2. So if I have 2 hydrogens with a mass of 2, that's 4 plus my 16. That gives me a formula mass of 20 grams per mole. So it's heavy compared to regular water, and it can absorb more energy. So that's all heavy water is. People also want to know, is it dangerous? Is it radioactive? Yes, it is. You wouldn't want to drink tons of it, but it takes large quantities of it being ingested for it to be dangerous to you. I wouldn't recommend drinking a glass of heavy water, but I don't think drinking a glass of heavy water would kill you either. So there's the answer for that one. Nuclear power plants, as we start to get lower in our fossil fuels, are going to become more prevalent. So you should know the pros and cons of them, and we will talk about this more detailed in class instead of listening to me talk about it here on the lecture. But pros of nuclear power plants: they use small amounts of fuel, they make a lot of electricity, the electricity is very cheap, and it's very efficient. The cons of nuclear power plants are the radioactive waste problems. So once the fuel rods are no longer concentrated enough to really make good amounts of energy, you need to put them somewhere and store them. The byproducts that are made are radioactive. This coolant water that's surrounding this reactor and used to turn your turbines has to go to cooling ponds and be held because it is also radioactive. It picks up electricity. You have the dangers of a meltdown. If a coal power plant burns, it's bad for the air pollution, but it's a temporary type of situation. If a nuclear power plant has issues, now you have a long-term, large-scale problem. So fission looked like it was going to be the answer for cheap electricity and the fuel problems, but the storage problems with the radioactive waste when you're done has made it more of a problem than people thought it was going to be. What currently looks more promising as an alternate power source that would have fewer problems is fusion. So fusion is the 4th type of nuclear reaction you need to memorize, and that's 2 small atoms being joined together. This is what's happening in the sun. It is typically 2 hydrogens producing a helium. When they talk about fusion, this is what you're looking for. Sometimes you will see a fusion reaction like this, where I have deuterium, so the hydrogen isotope that has a mass of 2, and tritium, which is a hydrogen isotope with a mass of 3, turning into helium and having an extra neutron. You will sometimes see the fusion equation as just 2 deuteriums turning into a helium. It's difficult to do. Okay, so it's happening in the sun. The reason why you have the sun and stars can do fusion and it's hard for us to do here, remember, hydrogens have this proton and the isotopes will have a neutron in the middle, and they have this cloud of this electron zipping around the outside. So if you have 2 of these things and now you want to push them together and get those protons in the middle to fuse, you have to get the 2 electrons past each other. and like charges repel. So now you need enough energy to get the two orbitals to overlap. And then once you get them to overlap, if you can get this to happen, enough energy, you remember, think of pushing two magnets together, their north poles past each other together. Now you have to get the two protons, the two nuclei, to smush together and not just overlap, but actually be pushed tight enough together so that they fuse into one piece. It takes extreme amounts of energy to get this to happen in the first place. Once we get it to happen, it should produce huge quantities of heat. So the energy input in the first place will more than be made up for, and once it gets started, it should be continuous as long as you keep adding hydrogen fuel to it. It should make enough of its own heat to keep the reaction going. We have to get the reaction started in the first place. Okay? The other thing that happens is if you have these extreme heats, what kind of container do you put this stuff in? So you have to have some kind of container that can withstand the heat of basically the sun. And so they're not using a material, they're not using matter, they are actually trying to use electromagnetic energy to make an electromagnetic bottle, they call it, to contain it inside of so that the material itself doesn't melt. They actually are getting closer. I used to think I would never see fusion power plants in my lifetime, maybe my children's, but not mine. But there is a multinational organization who is making large amounts of progress on this. So ITER, if you want to know more about it, you can go to iter.org. Here they have a little intro about what fusion is. So if you see their pictures, here they have deuterium, so our one proton and one neutron making hydrogen with a mass of 2. And here they have their one tritium, so they're one proton and 2 neutrons, giving this hydrogen a mass of 3. And they're smushing them together, making their one helium over here, 2 protons and 2 neutrons, and their one neutron left over. The machine itself is being built in France, and this is what it looks like. So you can also come here if you're interested in fusion at all, or physics. You want to be a nuclear physicist. And it will scroll over and it will tell you what the different parts are, and you can learn different information. There's the magnets they're using to make their electromagnetic bottle. This is a cutaway version, obviously. It's a round circle. In this inner chamber here is where they want the fusion to happen. It's really cool, really neat, and starting to be working. They're starting testing on it now, and hopefully we will see fusion reactors. If they can get fusion reactors started and working, reasonable and safe, they will eventually pay for themselves, and within the matter of a few decades, electricity will become extremely cheap. So we have to get the plants, the research for the plants done first, but eventually they would become really cheap, and your only byproducts then are helium, which is an inert noble gas, and some neutrons. Not a problem with storing or disposing of this stuff, and your raw materials are the most abundant element in the universe, so that shouldn't be a problem either of running out of them. To wrap it up, you need to memorize those 4 types of nuclear reactions. You memorized 4 types of inorganic reactions. Memorize the 4 nuclear ones. There's natural transmutation, one reactant turning into a new element. There's artificial transmutation, one element and one particle turning into a new element, so 2 reactants. And then under artificial transmutation, we have fission, which is the one with uranium plus a neutron. And then fusion, which is 2 hydrogens making a helium. Make sure you can memorize and identify those, and then those are all you need to know about nuclear reactions. Know that you add up the masses and the charges top and bottom and use your periodic table to figure out the missing pieces. The last part for this unit is going to be half-life in lecture E.